Hello physicists, welcome to our March 26th edition of Physics. This week we finished up our momentum unit and moved on to talking about rotational motion. So the two main things that I want you to leave the momentum unit with are the impulse momentum theorem, where we say that a force times a time changes your momentum, changes your mass times your velocity. That's where you have an external force acting on one object. On the other hand, we have a different class of momentum problems where we consider a system that's self-contained. So for instance, a bomb or something like that. And it blows up and all of the little pieces fly out. But if you add the mass times velocity vector of all of the pieces afterwards, they add up to be the same as the mass times velocity of all the pieces beforehand. And so that is a system where you have no external forces. The sum of the forces on the center of the mass equals 0, and therefore you have the initial momentum is equal to the final momentum. Okay, so we have impulse momentum and momentum conservation. The other important thing that we started this week was starting to talk about rotational coordinates. And the reason this was important, just to recap what we talked about in the last video, is that if you have a point, 2 points on a disk, the point on the inside is going more slowly than the one on the outside. In real terms, if it's a spinning disk, in meters per second, this is going slower than the thing on the outside because this is covering more distance in the same amount of time it takes to go around the circle. However, we can introduce what we call radian or angular coordinates, where we're measuring things in terms of radians, and in terms of radians, these 2 points are going around the same angle in the same amount of time. So they have the same angular displacement, they have the same angular velocity, they have the same angular acceleration. And that can be helpful if we want to apply, for instance, our constant acceleration model to angular spinning type of problems. So as I said, I'm trying to do a little bit of review for the quiz today. So let's go back and do it a little bit more slowly now. Okay, so the first type of problem you might run into is something like this, where you have an impulse creating a change in momentum. So the classic example is a bat hitting a ball. And so if you have your average force times the amount of time, it equals mv final minus mv initial. Okay, so that's your impulse momentum theorem. Not too hard to apply, but it's just a matter of remembering when to apply it. Okay, our other types of problems that we really spent quite a bit of time on was one ball comes in, another ball comes in, and then they go out. And they might stick together, they might bounce off each other. Now, we had two types, we categorized these types of collisions in two types. One of them was elastic. And what elastic meant was that, well, for one thing, they're bouncing off each other. Okay, that's true. But the definitional thing is that if you add up all of the kinetic energy at the beginning of this interaction, it's equal to the kinetic energy at the end. On the other hand, for inelastic, the typical thing is that the initial kinetic energy is less than the final kinetic energy. And you know, overall, in the whole universe, the energy is conserved, but the fact is that some of that kinetic energy, that it was kinetic energy of the bulk motion of the object, has been transferred to the microscopic kinetic energy that leads to the heating of the object. Okay, and the other thing that we talked about was a bit about rockets. And so if you have a rocket out in deep space and you want to speed up or slow down, what you have to do is fire out some mass. Okay, so by having a little piece of mass in the exhaust times the V of the exhaust, that has to be compensated by an increase in momentum this way. So if you have conservation of momentum, the exhaust pushing out the back has to be compensated by the increase in momentum of the rocket. So they go opposite directions. It's not a factor of pushing off the air or anything like that. Okay, so let's do, just for fun, a problem with momentum. Or rather impulse. It says we have a force that varies with time and is applied to an object. So there's force, there's time. It says the force increases linearly from 0 newtons to 24 newtons during the first 2 seconds. 24 newtons, there you go. Then the force remains constant for 4 seconds. So there's 6 seconds. This is a span of 4 seconds, 2 seconds. And it just stays flat. Then, okay, during the last 2 seconds, the force linearly decreases to 0 newtons. Okay, so that's 8 seconds. That's another 2 seconds. It asks, what is the total impulse exerted on the object? Well, the impulse is the average force times the amount of time that it's applied. So we could go ahead and find our average force, I suppose. But in this case, it's going to be easiest just to use this definition. It's the integral of force times dt. And so that's just the area under this curve. Okay, and if you notice, this triangle is going to match up that space. So our total force is going to be, so you could do it just by adding up this triangle plus this rectangle plus this triangle, which this triangle goes on top of this triangle to make it effectively a rectangle of 6 seconds times 24 newtons. Which I believe is 144 Newton seconds. Okay, that was just for fun. I don't think there's one on the quiz that looks much like that. The tricky parts on the quiz, at least in my opinion, are the things that are new. So having to do with kinematic equations. On Wednesday, we covered quite a bit of material. And so we talked about how radians are basically, if you take the arc length that you've gone through divided by the radius, and then you can always convert from radians to degrees or radians to revolutions. So 2 pi radians is the same as going around your circle once. The other thing that's a little trickier is we said use your right hand. If you curl around in a counterclockwise direction, that gives you a thumbs up. So as a convention, just for a convenient way to label things, we have counterclockwise is plus and clockwise is minus. We also talked about how, okay, we would like to think about, instead of just angular speed or angular position and angular speed, we went from linear to angular coordinates. So if we had x, we said instead we're going to use theta, x in meters, theta in radians, and then we could have our v, our velocity in meters per second, and we wanted to think about having an angular velocity, which we're going to have as an omega, which is going to be in radians per second. And we also talked about having acceleration, meters per second squared. This is how much your velocity is changing. For angular velocity, it's going to be how much your angular velocity is changing, how your spinning is changing, and that would be in radians per second squared. And of course, you can always convert for a particular point on your rotating object from radians to linear just by multiplying by the radius. And because these have similar definitions, we can always go ahead and use a constant angular acceleration model and just replace all of our x's with thetas, replace all of our v's with omegas, and replace all of our a's with alphas. The last thing we talked about on Wednesday was that if you're going around in a circle, we've talked quite a bit about centripetal acceleration, but that was all for constant speed. Now we're going to talk about what happens if, and in that case, the v was always tangential, but the a was towards the center of the circle. And we call that our centripetal acceleration. What we added on Wednesday was the idea that we still have to consider that centripetal acceleration, the thing changing the direction at all times. And that's going to be v squared over r, which we showed is the same as omega squared times r. Okay, so that idea didn't change. But if your motion around that circle is getting faster or slower, then we do need an extra piece on there that has to do with this this alpha, this angular acceleration. And so if you wanted a total for any point on your object, if you wanted a acceleration vector for the object, you'd have to add together the tangential and the radial components as vectors. And then the magnitude of that acceleration would be given by basically by the Pythagorean theorem. All right, so here is just a quick example. It says a jet engine has an angular acceleration of minus 2.5 radians per second squared. Angular acceleration is alpha minus 2.5 radians per second squared. What does the minus mean? Is that clockwise or counterclockwise? Turns out that is clockwise. And it says, which one of the following statements is correct concerning this situation? It says, the direction of the angular acceleration is counterclockwise. The minus means that it's clockwise. The direction of the angular velocity must be clockwise. Don't know about that. We aren't told anything about the angular velocity. We know about the angular acceleration. So, unknown. The angular velocity must be decreasing as time passes. Well, if our object to start with was going counterclockwise, that would be true. But if it were going clockwise, it would be actually getting faster. You know, it's like negative acceleration is getting faster in the back, going backwards, or getting slower going forwards. So we don't really know. If the angular velocity is clockwise, now I can really make a claim, then its magnitude must increase as time passes. That I like. Okay, so if we're initially spinning clockwise, this will make our spin clockwise even faster. Yes. If the angular velocity is counterclockwise, then it's no, opposite of that. Okay, so that's just a quick example. Now, to practice for the quiz, I think that it's best for us just to do an example. And this is a literal homework problem that I gave you, so it's not wasting your time to go through this example. All right, it says a flywheel with a diameter of 1.20 meter is rotating at an angular speed of 200 revolutions per minute. So notice in problems that you'll get in this chapter, often part of the problem is just that I'll give you information in funny units. So for instance, here I give you the diameter. That's not really the useful thing to know. The useful thing is the radius. But of course, you can just get it by dividing it by 2. So the radius would be 0.60 meters. Okay, it's rotating at an angular speed of 200 revolutions per minute. Okay, well, let me try to remember what is the symbol for angular speed. It's got to be omega is 200 revolutions per minute. Now that's not the most useful type of way I could write it. It first asks me, what is the angular speed of the flywheel in radians per second? Well, I've got to do some unit conversions here. To go from revolutions to radians, 1 revolution is 2 pi radians. Okay, that's 1 time around the circle. And from minutes to seconds. So 1 minute is 60 seconds. Revs would cancel out, minutes would cancel out, and I would have an answer in radians per second. Okay, now let's see what they ask next. It says, what is the linear speed of a point on the rim of the flywheel? Okay, now the thing to realize is you have to do that part A where we found the omega is 200 revs per minute. Oops. 1 rev, 2 pi radians. Okay, so once you have this in radians per second, then it says, what is the linear speed of a point on the rim of the flywheel? Once you have this already in good units, that becomes an easy question, because then the V is just that omega times R, which as we said is 0.60 meters. If it's in the wrong units, it can be tricky. So that's really the whole game here. Now part C asks, what constant angular acceleration in revolutions per minute squared would increase the wheel's angular speed to 1,000 revolutions per minute in 60 seconds? Okay, so here we have our initial angular speed is 200 revs per minute. And our final angular speed is going to be 1,000 revs per minute. Okay, so you're getting much faster within the course of your time, which is 60 seconds. But it might be helpful for me to write this if my time units here are minutes. It might be helpful to write this in minutes. So 60 seconds, 1 minute, 1 minute. Okay, and then it asks, what constant angular acceleration in revolutions per minute squared will increase the wheel's angular speed to 1,000? Okay, so I could use the final angular velocity equals the acceleration times the time plus the initial angular velocity, and just find this. Okay, so just notice the only challenge here is that you've got minutes, minutes, minutes. If you do that, you're going to find, just plugging those numbers in and doing your algebra, it's going to give you an alpha that's in revolutions per minute squared. But if we had stuck in 60, we would have gotten nonsense because we would be mixing units. So you got to be vigilant. Okay, and then finally the last question is, how many revolutions does the wheel make during that 60 seconds? Well, remember, it's not just spinning at the same rate the entire time. It is accelerating, so we would have to use our accelerated motion. So the angular position equals 1/2 alpha t squared plus the initial velocity times time plus the initial position. Okay, so in our previous slide we found this. We know this would be 1,000 revs. And this was some answer in revs per minute squared. Omega naught was 200 revs per minute. And all you have to do is put in your t. And the t that they give you is 60 seconds. However, remember, if everything here has minutes on the bottom, you better make sure your t also is in terms of minutes. So in that case, it would have to be 1 minute. Okay. So if you put in just 1 there, you'll get the right answer. But I am a little nervous about today's quiz, and the reason I'm nervous is because it requires you to do a little bit of vigilance, making sure that your units match up. Other than that, there's no tricks, but it does. You do need to make sure that you're not mixing different types of units. Okay, so today, 2 ideas that we're going to introduce in this video. One is that of angular velocity vectors, and the other is moment of inertia. So angular velocity is just all about looking at, for your axis of rotation, looking what direction is my object spinning around, and then if you use your right hand, your thumb will point in the direction of the angular velocity. So we're going to represent that angular velocity as a vector, and you get it using your right hand rule. So that's one idea. The other idea is that of a moment of inertia. The way you get your moment of inertia is by adding up the mass times the distance squared from the axis of rotation. So this r is how far is your object from the axis of rotation. And you'll remember before we had our kinetic energy is 1/2 mv squared. That is still true, but it's not so useful. A more useful way to write this is k is 1/2 I omega squared. So this v in a spinning object is different for every single radii. So out here the v is bigger than in there. This omega is the same for the whole spinning object. So all of the differences in the velocities are taken into account in this this strange new concept, the moment of inertia, or the rotational inertia, same thing, that has units of kilograms times meters squared. Okay, so first off, I'd like to say one caveat, which is you might say, okay, there's a vector for angular velocity, so there's probably a vector for angular displacement, right? No, there is not. Why is there not? Well, the reason is that for vectors you want a plus b, so even if you had xyz plus xyz, you'd want to be able to add them in either direction. That's not true, however, for angular displacements. If you rotate in one direction and then another direction, or if you rotate in another direction than the one direction, you end up with different orientations of your three-dimensional object. So you need to be careful with this. If you go on in physics, you'll find out that there are ways of dealing with this. They involve 3x3 vector or 3x3 matrices called rotation matrices. You can also do it with 2x2 complex matrices and a 2x2 or a two component complex vector. Both interesting. Those are called spinors. And the other way, they call it SO3, the orthogonal, special orthogonal group of 3 dimensions. Okay, whatever. In any case, we're not going to do it in this class. In this class, we're going to just say, don't use vectors for angular displacements, but do use vectors for angular velocities. Now, I could attempt to explain this, but I think this guy's video is fantastic. And so I encourage you at this point to pause my video and go watch his. And I've put a link to that in your PowerPoint. So please pause this, go watch his video. Use your hand. I know if you're watching this video, you are in the privacy of your own home. And so you don't have to worry about other people, looking at you. So please go ahead, do the exercises, and he'll explain it beautifully. You go around the circle, and then your thumb will be pointing in the direction. Okay, so I really pause, go watch it. All right, we're back here. Let's do some practice here. So you've practiced now with the video. And let's try it on ours. It says the wheels of a bicycle roll without slipping on a horizontal roll. The bicycle is moving due east at a constant velocity. North, east, south, west. Yes, what is the direction of the angular velocity of the wheels? Okay, now I want you to actually try it. Go ahead. Orient your body. Use that right hand of yours. I'll do it by myself. East. The wheel would be rolling like this. My thumb is pointing north. Okay, so it's very physical. When you're taking your test, I expect for you to go and watch you do a little bit of dancing. All right. Okay, let's try one more. Okay, now imagine yourself. You're the character in this story. While putting in a new ceiling, Jake uses a drill to put screws in the drywall. The screws rotate clockwise as they go into the ceiling. What is the direction of the angular velocity of the screw as the drill drives it into the ceiling? Express the direction relative to Jake, who is looking upward at the screw. Okay, so you're Jake. You're looking up at the screw. You do your righty-tighty, lefty-loosey. You go tight, tight, tight. Okay, so it's going around like this. You take your right hand and you go vroom. And you're down here, and you say, oh, it's pointing up relative to me. Okay, so hopefully this is a little less confusing now that you've watched the video and you've done a couple of examples. The other idea that I want to introduce to you today is that of the kinetic energy of a spinning object. Now, as I said, all we're doing is we're adding up the mv squared of the different parts. So for instance, let's say that I had 3 objects and they're on these massless rods. So all the mass is just in my M1 at R1. I've got M2 at R2 and M3 at some distance R3. And it's spinning around the center right there. Well, how would I find out what my kinetic energy is of those three objects? It would be, the kinetic energy would be 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared. Now, assume that these are all in a rigid object and they have some rotational speed. Well, the omega is different, is the same for the whole object. It's all spinning at one rate, but the r's are different for different parts of the object. So in that one, it would be k equals 1/2 m1, and then this would be r1 omega. So r1, it's not omega 1 though, it's omega for the whole object. It's 1/2 m2 r2 omega. Same omega, even though the r's are different. 1/2 m3 r3 omega. Okay? So I'm just adding up 1/2 mv squared. Now I'm representing that by using the rotational speed omega, the rotational velocity. Now, the omega squared is going to be in every one of these terms, so I get to factor it out. Okay, so I'm going to write this as k equals, and there's a 1/2 in each one of these, so I'm going to factor that out too. It's going to be 1/2, and then a bunch of stuff times omega squared. What's that stuff going to be? For the first term, it would be m1 r1 squared. For our next term, it would be m2 r2 squared. For our next one, it would be m3 r3 squared. Okay, so what we've done is now we say this is, instead of 1/2 mv squared, this is 1/2, and we call this whole thing I. And notice what it has to do with is how these masses are distributed throughout my object. So my total kinetic energy is 1/2 I omega squared. So I depends on what I use as my rotational axis, and it depends on the geometry of my system. So, okay, I, for whatever number of masses you have, it's always going to be m times ri squared. K is going to be 1/2 I omega squared. However, it does matter where you choose your axis of rotation. So for instance, for a rod like this, if you're spinning it around just like this, like a, doing a straw between your palms, that's easy to rotate because the r is small for all of the mass. The moment of inertia for this would be very small. On the other hand, if I'm trying to spin something this way, it's a little bit harder because the masses are further away from the axis of rotation. So this would give you a small I. This would give you a bigger I. Same object. The difference is that you've chosen a different axis of rotation. Okay, on Monday we're going to extend that idea to using integrals. But not today. Let's just do one quick example, and this should be enough to get you through your homework. So it says figure 1033 gives angular speed versus time for a thin rod that rotates around one end. The scale on the omega axis is set by omega s equals 6 radians. So this is 6, 1, 2, 3, 4, 5, 6. I guess this would be 7. And this is going just 1, 2, 3, 4, 5, 6. Okay. It asks, what is the magnitude of the rod's angular acceleration? Okay, well, I know what my speed is. My angular acceleration is just going to be my omega final minus omega initial over t final minus t initial, just like it would be for regular old acceleration if these were velocities. So my final, it looks like it's 7 radians per second minus, my initial is -1 -2, -2 radians per second, all over, how much time did that take? 6 seconds. Okay, so this would be 7 minus -2, so that'd be 9 over 6 radians per second squared. Okay. And then it asks, at t equals 4 seconds, the rod has a rotational energy of 1.4 joules, or 1.6 joules. Okay, so this is going 4 radians per second. So for part B, it says when omega equals 4 radians per second, the rod has a rotational kinetic energy of 1.60 joules. So K equals 1.60 joules. And it asks, what is the kinetic energy at t equals 0? Well, what I would have to do here is I would say K at this point is 1/2 I omega squared. So you know K, you know omega, you need to find I. Then it asks, what is the kinetic energy at t equals 0? Well, if you look at t equals 0, you can find out what the omega is at that point, because your omega is going to be omega naught. So that, wait, what am I talking about? What is its kinetic energy? Sorry, I'm overcomplicating that. At t, what is its kinetic energy at t equals 0? Well, it's at t equals 0, you have omega equals -2 radians per second. So if you have omega equals -2 radians per second, you could use this formula again, 1/2 I, once you have that I, times omega squared, -2 squared is +4, and there you go. You could find your K. All right, so that's the sort of reasoning that you would use in that problem. So we'll do more of those types of problems next week. Now I should say, in class, I remembered that we don't have a full week of school next week because we have Easter break on Friday and Monday. So, homework, if you want to give it to me on Monday, you can give it to me on Monday. If you want to give it to me on Wednesday, that's also okay. What is due this week is the quiz. So please focus on the quiz this afternoon. That's the thing you want to get done tonight. So what are our big takeaways? Angular displacement is not treated as a vector. Angular velocity is treated as a vector. Direction of angular velocity is determined using the right-hand rule. And the kinetic energy of a spinning object is K equals 1/2 I omega squared. All right, so thank you for watching and have a great weekend.